Hello everyone. So let's now solve practice assignment week 8 question number 3. Which of the following options are true? So let's look at each option one by one. Option 1. Option 1 says let U, V and W be three vectors in R2 and this defined as the inner product on R2 if inner product between U and V is same as inner product between V and W, then V is equal to W. So for this option, consider three vectors that U to be 1, 1, V to be 2, 1 and W to be 1, 2. If we consider our inner product to be the standard dot product for the case, if we take the inner product between U and V, while consider this to be our dot product, then 1, 1, 2, 1 and that would be 2 plus 1 equal to 3. And while if we take the dot product between U and W, we will get 1, 1 with 1, 2, that would be 1 plus 2 and that is also 3. Now we can see that the dot product between UV and dot product between V and W are same, but our V and W are not same. So that means this option is false. Now let's look at second option. Let V be an inner product space if inner product between U and V is equal to 0 for all U belonging to V, then V is equal to 0. So option 2, we have given that inner product between U and V is equal to 0 for all U in the vector space V. So that means there will be some vector, that means for V, if we take the inner product of V with itself, that would also be 0. And we know that this can only happen when our V, small v, is 0. So as inner product of U with V for any U that belongs to the vector space V is equal to 0, and that means the if U can be equal to V, for this case also it would be 0, and from the property of inner product we know that this can only happen when V is 0. So now let's look at option 3. Let V be an inner product space UV belongs to V if inner product of U plus V with U minus V is equal to 0, the norm of U is not equal to norm of V. So we have given that inner product of U plus V with U minus V is equal to 0. So from the bilinearity property of inner product, we can write it as inner product of U with U minus V plus inner product of V with U minus V equal to 0. And furthermore, we can simplify it. U minus inner product of U. Okay, let's keep it as U with negative V. Now here this we are multiplying with negative 1, and again we can use the bilinearity property. So it will be inner product of U with U minus, so minus 1 times inner product of U with negative, U with V plus inner product of V with U and minus inner product of V with V, and that is equal to 0. We can cancel out these two quantity, as we know due to the symmetric property of inner product of UV would be same as inner product of V and U. So these two ways will cancel out and we will left with inner product of U with U minus inner product of V with V is equal to 0. Now The inner product of vector with itself is nothing but the norm square minus norm of v square equal to 0, and from that we get, and that is norm of u is equal to norm of v. So this is the result that we get, while in the option it is saying that norm of u is not equal to norm of v. So it is wrong. Now fourth option, let V be an inner product space if S belongs to V, then S per is equal to the perp of span of S. So option 4. So we have given that we have some set S. Let's consider this, that it contains some vector v1, v2 till vn. Now we have to prove that the perp of S is same as span of S and the perp of. This means it is the orthogonal complement of the set S. That is, if let's say we have some vector W that belongs to the S per, then inner product of any vector from the set S with W would be 0. So this is what it is meant by S per, that is the orthogonal complement of the set S for all Vi in the set S. So I equal to 1 to n. Okay. Now let's consider the set a vector x that belongs to the span of S. Now we can, what is the span of S? Span of S is nothing but the linear combination of the vector. So our vectors are v1, v2, vn. So its linear combination, let's say some coefficients a1, v1 plus a2, v2, like that, and vn. So this is the span of S. So now if we take the dot product of this vector x with the vector w, that is the vector which belongs to the span of S, then this would be, now we can write it as x is the linear combination of the vector that belongs to the set of S, as x is the span of S. So a1 v1 plus a2 v2 an vn with w. Now again with the help of bilinearity property of inner product, we can write it as a1 v1 with w plus a2 v2 with w and vn with w. Now we can take this coefficient outside, so it would be just the inner product between v1 and w plus a2 times inner product with v2 and w, and so on. Now as we know that w belongs to the S part, that is the orthogonal complement, and this v1, v2 till vn, they belong to the set S, and we have already uh, given that as W belongs to the set of W belongs to S per, that means any vector in the set S would be orthogonal to the vector W, that is inner product of Vi with W would be 0 for any vector in the set S. So these all inner product would be just 0. So we get A1 times 0 plus A2 times 0 and so on, n times 0. So this would be all 0. So as we got this as 0, so that means the span of S and the orthogonal complement of this is same as the orthogonal complement of the set S. Now option 4. So this we have gotten as correct. Now last option. Suppose u1, u2 till un be an orthogonal set of vectors in an inner product space V, the norm of u1 plus u2 till square is equal to norm of u1 square plus u2 square till norm of square. So we have given that the set u1 till is an orthogonal set. That means uy with uj for I not equal to j would be equal to 0. Now, what we have to check here is the norm square of u1 plus u2 till is the famous summation of individual norm square. So we have to calculate the norm square of u1 plus u2 till and that is same as the inner product of u1 plus u2 till with u1 plus u2 till and with the help of bilinear property we can write it as u1 inner product with u1 plus u2 till plus inner product of u2 with u1 plus u2 till and so on. We can write it as with u1 plus u2 till and again we can write it as u1 inner product with u1 plus u1 inner product with u2 and for this we will write it as u2 inner product with u1 plus u2 inner product with u2 and so on. Now notice that as it is already given that the set is an orthogonal set, that means inner product for uh, vectors between each other would be 0. So that means inner product between u1 u2 would be 0, u2 would be, u2 u1 would be 0, except only when we are taking the inner product of the vector with itself, all other inner product would be 0. And we know the inner product of vector with itself is the norm square of the vector. So it would be norm square of u1 plus this quantity would be 0 and here for this everything would be 0 like inner product of u1 with u3 or with would be 0. Similarly for here and similarly for all the remaining. In the final we will get this norm of square and that is what it is given in option. Hence it is the correct answer. Thank you.